Okay, do let me know in the chat if you can actually see this, because I think for some reason the last... Okay, can people see me? Let me just see what's going on. For some reason OBS, which I'm using, just crashed. It hasn't done that before in the other lives, so can people there actually hear me at the moment? Let's see. It's probably going to be like an Edexcel part 1, Edexcel part 2. So yeah, do let me know if you can actually hear what I'm saying or if I'm just talking to myself. And yeah, you can hear me? Can you see me as well? Okay, Jack, back up, Prem, Thana, Matthew. Okay, I don't know what happened. That's it. Maybe Edexcel shut me down because they know I'm teaching stuff. Okay, so I don't know where we got to. Basically, if we've got these two waves here, the red one, where the two things meet, this has gone through 1 3/4 of a wave of wave cycles. But one at the bottom's gone through 1 1/2 wave cycles. So basically, the difference in the path is going to be equal to 1/4 of a wavelength, and obviously that unit would have meters. Okay. The next one then is if we look at the phase difference, well, 1/4 of a wave cycle is going to be equal to 1/4 of 360, and therefore that's going to be equal to 90 degrees. So the two waves here, one of them's kind of in the middle, the other one's at the bottom, and therefore their phase difference is equal to 90 degrees, or indeed pi over 2 radians. Okay, right. There we go. So that one there is a little bit about the difference between those two terms. Right, the next bit is about stationary waves. Shall I do that? I'm going to do stationary waves on the next page. Okay, so that's kind of the first bit of waves. Of course, if you want to screen capture it, now's the time to do a screenshot if that's useful. So often, when we talk about waves, we tend to look at progressive waves, which are transferring energy or information from one place to another. The other type that we have is stationary. So they can be called stationary. They can also be called standing waves. And basically this is where maybe we send a signal maybe in one direction. It meets a fixed end, and then it's going to go back in the other direction, something a bit like this. Okay, and if you send this wave along and then you send another one, they start to interfere with the waves coming back in this direction, and then what we get is a wave that might do something like this. Okay, and that's what it looks like. You might have maybe a fixed end over here, and then maybe half a wave cycle later it looks like this. Okay, so this is a very poor picture. We get other ones as well, so you might get one that just has something like this. Okay, and of course there are many more. Now the points where you have no displacement are the nodes, and if you've got something like a string, then it's going to have a node at each end. This here also has a node in the middle, and then you've got a point where we get the maximum amplitude. Hopefully people can see me in the chat. Just let me know this is all working, because I hope it's not crashed again. Yeah, is that working? Cool. So the other thing is that, so basically this is like one position over here. That's another one. And the points where you get maximum displacement are the antinodes. Okay, so there's some standing waves for strings. So the speed, if you have a transverse wave on a string, the speed of that wave, and this is like at the moment just looking at string, the speed of that wave is equal to root t over mu. And this is going to be the mass per unit length. Okay, so there's a relationship between the tension in that string and how heavy that string is in terms of the mass per unit length, and that's going to give us the velocity of that wave. Okay, so the next one, Core Practical 7, is about the effects of length, tension, and mass per unit length on the frequency of a vibrating string or wire. The standard way that this is done is you have some kind of signal generator over here. Okay, Often you have maybe a retort stand. You attach a string to it, and then that string goes along, it goes over a pulley and off the edge of a desk. Okay, so that's our pulley there. And what we get is we can set up different fundamental frequencies, and what you get is a wave that might oscillate a bit like that. Often it's best to tie the string to the retort stand. Okay, and then you've got the vibration generator attached onto that string, and that means that the actual oscillating bit of this vibration generator isn't being pulled to the side by the tension. Of course, we can add a mass over here, and that weight is going to provide a tension in the string, which is the tension we're looking at. The other thing that we can have over here is the thing called a bridge. Okay, so the bridge, a bit like a bridge on a musical instrument, gives a definite endpoint, and that means we can measure the length of that standing wave. Okay, Alexander, will the VODs be saved in the playlist or on the website? I'm not quite sure yet. So I reckon I'm going to put them on, they'll definitely be on my website, alevelphysicsonline.com. Okay, so yeah, for some reason this kind of had a break, but you know, I'll have like I'll probably call it part 1, part 2 and so on. So we can adjust the weight and therefore the tension. The length is going to be there, and then the mass per unit length, you just measure that by basically getting your bit of string, you put it on a mass balance, and therefore you know that maybe a 2 meter long bit of string or a piece of wire that's 2 meters long has a certain mass, and therefore you can work that out quite accurately. And of course you can vary this, you can vary this, and you can vary this. So you can apply different things here to like look at maybe, and obviously you can record from here the frequency, and if you know the frequency and you know the wavelength, that allows you to work out the wave speed. Okay. Now the important thing to note is that from a node to a node is equal to half a wavelength. If we think about this standing wave here, a wavelength goes from here, it goes up, down and up again, and that means the distance between a node and a node must be equal to half the wavelength. So hopefully that helps. Again, this is just like one way of doing it. So there might be a question about this or some variation of it. The next bit is we're looking at, okay, there's a load of stuff here. So the next bit is looking at the intensity of radiation. The intensity of radiation is equal to the power divided by the area. So the way I'm often thinking about this is if you have maybe a light bulb, for example, the power is going to be the energy transferred per unit time. And of course, as you go further away, it's going to become less intense because that energy that's being emitted every second is going to be spread over a much larger area. Now, this equation here often links to the surface area of a sphere, because what we're thinking about is this kind of maybe 1 over r squared relationship, where if you go twice as far away, the area is going to go up by a factor of 4, and that means the intensity is going to go down by a factor of 4. So this equation here is often linked to a 1 over r squared relationship. We then have quite a bit about refraction. Now, refraction isn't just to do with light, although light is the most common thing that we use. So I would say that in terms of refraction, it can be all sorts of waves that refract. So it can be, you know, waves underground that refract through different types of rock. It can be different parts of the electromagnetic spectrum, but most of the time we tend to talk about light. Now, if we have maybe medium 1 out here, and then we've got medium 2 in here, and we maybe look at the path of a wave through these two things. Okay, so maybe this wave slows down as it meets the boundary. What we can say is that, I'm just going to do it in different colours, n1 sine theta 1 is equal to n2 sine theta 2. Okay, and looking at this diagram here, if we draw in the normal at 90 degrees to the surface, again, that's just GCSE knowledge, we've got theta 1 up here, and then down here is where we'd have theta 2. Okay, now I think that's good. A lot of the time though, we talk about something going from air into glass, and at that point N1 is just 1, so the refractive index of this is just 1. And then we often then say that sine of the angle of incidence is equal to N2 times sine the angle of refraction. And therefore the refractive index of these two things, N, is just equal to sine I over sine R. Okay, so that's the simplest form when we have, I'm just going to put this with an asterisk up here. This is maybe like air to glass or something, or air to plastic. So this only happens if you've got air, where N1 is equal to 1. Okay, some people asking about significant figures. I would say use the least, your final answer, not your rounded down. Basically, your intermediate answers, you need to keep as many significant figures as possible. But for your very last kind of answer that you write in like the kind of little answer space, I would say use the least number of significant figures given to you in the question. If you're not sure, go to 3 significant figures, because they're not going to drop you loads of marks over the paper. If you're not sure, just go to 3 significant figures, but it should be the least number of significant figures in the question, which tends to be 3 anyway. Okay, so yeah, so that's refraction. We also have a critical angle, and this is where maybe you've got something which has got a high refractive index, so I'm going to call that material 2. Material 1 has a lower refractive index, and if you've got something hitting this at a large angle, then effectively the angle of refraction would be 90 degrees. Okay, and above that we then have all of that light, or whichever kind of wave, being reflected back in. Okay, so looking at this, we can say that sine C, and Edexcel use a capital C to represent that critical angle. Sorry, the critical angle is when all of that refracted light comes out along the boundary. So sine C here, this is when sine C is equal to 1 over n. Okay, now of course, if the angle is bigger than the critical angle, we then get total internal reflection. Okay, so basically if the angle theta is bigger than the critical angle, we therefore get total internal reflection. Okay, hopefully that's helping. Hopefully some of you might be finding this useful. Do let me know if you're watching. I might well just be talking to myself on my own in my studio. But yeah, that's total internal reflection. How to measure the refractive index of a solid material, point number 74. Basically, this is a GCSE practical. If you want to measure the refractive index, then what you need to do is you need to set up maybe a glass block or a glass semicircular block. You use a ray block, you put it on some paper, you measure out the angle of incidence, you measure the angle of refraction, and then what you're going to do is you're going to look at various angles of incidence, various angles of refraction, and if you put them on a graph where you've got sine I up here and sine R along there, then the gradient is going to be equal to sine I over sine R, which is the refractive index n of that material. Okay, what if theta is the same as critical angle? Okay, so if theta is equal to the critical angle, then all of the light moves out along the boundary. Okay, so basically that means all the light hits this and it goes out here. The reason being that at the critical angle, looking at this equation here, we know that sine I equals n2 sine R, and what we could then say is that if R is equal to 90 degrees, sine R is equal to 1. Okay, and basically you then have so sine, is that right? So basically sine I is equal to sine R over n1, and sine r is going to be 1, so sine I, the angle of incidence, is going to be equal to the critical angle, which is equal to sine r, which is 1 over n. Does that make sense? Hopefully. Yeah. Hopefully that helps, Jack. Might just be... I probably should have had like some more... I do have videos about this, but I think basically from this equation up here, we say that, yeah, sine theta 1 is the same as sine c, and n2 is going to be 1, sine theta 2 is 1, and therefore you've got sine c is equal to 1 over n. Okay, right, that's a bit about refraction. Let's keep moving on. Got quite a few more things to do. Right, we then have some stuff about lenses. Now again, I've got some videos about lenses over at A-Level Physics Online. If you go to my alevelphysicsonline.com/edexcel, you can find the videos there. You need to know about the word focal length for converging and diverging lenses. So if you've got a converging lens or you've got a diverging lens, I'm just going to use these symbols. You've got your principal axis through the middle, okay, like that. And basically, where the rays of light, on this one, I'm going to do the rays of light in purple. If you have parallel rays of light, they will all diverge, or converge, sorry, to this point here. So this point down here is going to be the focal point, and this distance over here is going to be equal to the focal length. If you've got a diverging lens, then parallel rays of light, or rays of light parallel to the principal axis, they will diverge, but they appear to come from this point over here, like that. And of course you always need to add the arrows on your rays of light to show which way it's going, like this. Again, this point here is going to be your focal point, and this distance here between the lens and that is going to be equal to your focal length f. Okay. Right, the next bit then. Yeah, so they're the kind of simple things. Now, I think when you're doing diagrams to look at the position of images, there are three to look at. There's really objects far away from a converging lens, objects close to a converging lens, and then objects in diverging lens. So this is, and I think as well, what you need to do is make sure, I'm just going to do this freehand, okay? So here we've got our focal point, we've got the lens, okay? And if you have something a long way away, so I'm just going to use a green arrow, okay? Now I think you only really need to draw two lines. You basically draw one line which is going to be parallel to that principal axis, and that then goes through the focal point like that. Okay, so that's the first one I'm going to draw. I'm going to do that one in purple. We draw another line that goes from the top of this through the centre of the lens, and because it's going through the centre of the lens, the parallel sides of that lens means that the ray of light that comes in is going to be parallel to the ray of light that comes out, and that means it's going to go straight through the centre like that. Okay, and it's where the two lines cross over is where we're going to have the top of the image. So that's going to be the top. Now anything from the bottom, a ray of light leaving the bottom is going to travel straight through the centre and keep going. So that's going to be the bottom. And now what we have here is an image. This was the object over here, but we can see it's now been inverted. It might be diminished, or it might even be the same size or enlarged depending where it is, but it's upside down, it's inverted, but it is a real image that can be projected onto a screen. Okay, thank you, Ms. Raff. Yeah, I am your physics teacher, I'm just your virtual physics teacher. So that's an object a long way away. If we have something similar, and we've got the same lens, we've got the same focal length, but now the object is closer than the focal point. Of course, there's going to be a focal point on both sides, because just like light can go this way through, it can go that way through as well. So we maybe have a focal point there. We're going to do the same construction. So the first ray of light hits this and goes through the focal point like that. The second ray of light goes through the centre. But now these two rays of light appear to diverge, and they don't actually cross. But if we're to follow where they appear to come from, I'm going to do a dotted line to show that this is a virtual ray. They appear to cross over up here. And what we now have is an image which is much bigger than the object. but this time it's formed by virtual rays of light and it appears to come from over here. So this is what we call a virtual image. Okay, it's enlarged, and this is like maybe where you have a magnifying glass or something like that. Okay, the next type that we have is going to be this one over here. Again, I'm going to draw this out one more time. So now we've got a diverging lens. We might have an image over here. We're going to have a focal length. I'm just going to put a dot on each side. We do the same construction method. So we have a ray of light which is parallel to the principal axis, and then when it goes through the lens it diverges, but it appears to come from this point down here, from the focal point. We have our other ray of light that goes through the centre like that, obviously drawing with a ruler and everything, and where the two cross over is down here. Now again, that's our image and that's our object. This one happens to be diminished, it's upright, but it's a virtual object as well. Okay, so just a few basic things there. Now the power is going to be related to how much that light bends. Okay, and the power of a lens is equal to 1 over the focal length. So what you can see is if you have only a very slightly lens-like thing, it's going to have a very long focal length and it's not going to be very powerful. Whereas if you have a shorter focal length, I can't really do this with my hands so well. If you've got a shorter focal length, we're going to have a much more powerful lens. Okay, and that's measured in diopters. Of course, it's going to have the unit of like meters to the -1 in SI base units as well. Now, if you've got multiple thin lenses next to each other, so maybe you had, this lens added to this lens, added to this lens, what they all do is they all kind of partake in kind of bending the light. So the light that comes in, it's going to be bent by this one and this one and this one. Okay, so each one kind of bends that light a little bit more, and their total power is going to be equal to the power of this one, plus the power of this one, plus the power of this one. And if you look at the distance between the height of the object and the height of the image, we've got two equations that you need to be aware of. That's 1 over u plus 1 over v equals 1 over f. Okay, and also the magnification is equal to v over u. Okay, where v is going to be the height of the image and u is the height of the object. Now the way I can remember that is a bit like if we're thinking about velocity, we've got our initial velocity and our final velocity, so u and v. So u is like the initial height of the object and v is like the final height of the image. And I think that's my way of remembering what v and u mean. But basically there's a link between this height over here, this height over here, and the length of that focal length. So again, that's kind of thing that I think that's kind of pretty much lenses summarized roughly. Does that help anybody? Do let me know. By the way, if you are liking this, make sure you do like the live stream. You do put some hearts in the comments or whatever. I think you can click that heart button. I'm just going to have some more milky tea. I know I'm spilling it on the page, so I've got some more milky tea to keep me going. Hopefully this is helping somebody. Okay, what is plane polarization? So polarization, yes it is helping, cool, Luke, awesome. So polarization, is it a Z or an S? Polarization in the UK. The tea is milky. Yeah, do you know what? Milky tea, you can't beat it. It's absolutely amazing, So yeah, that you might love it, you might hate it. I love it. Right, okay, so polarization, this happens only if you have a transverse wave. So you can't polarize a longitudinal wave. Often there's this picket fence analogy where you might think about maybe a wave, and I suppose a way to show it is, often we think about a wave kind of looking like this, yeah? We can also maybe draw that in like 3 dimensions. So this is a way to maybe represent an electromagnetic wave. So you've got the electric field in one plane, and in the other plane you have your magnetic component of that wave. So effectively, if you were to look at this end on, what we'd see is that this wave basically has, it goes up and then it goes down. So we're just maybe just going to consider the electric part of that wave, because every time you have an electric field that oscillates, we have an associated magnetic field oscillating. So basically this is a plane polarized wave. So it's just moving, the oscillations in the electric field are just in one dimension. Now if you've got something which is non-polarized, it's going to oscillate up and down. There'll be also some bits of the wave that are going left and right, that way and that way. So this is basically unpolarized. And if you pass it through a filter, then the only thing that comes out is the oscillations in that same plane. So often we have this picket fence analogy where you imagine a rope which is vibrating up and down. You can actually have that going through the gaps in a picket fence and it keeps going up and down. But if you had that wave in the rope going side to side, as soon as it went up to the fence, it would stop going through. Okay, so plane polarization. What else do you need to know about it? That's basically it, really, isn't it? Okay, diffraction. So diffraction happens when a wave goes through a gap. Now the simplest one is if you have a gap like this, or an aperture, let's get rid of some of that milky tea, and you send a wave through it. So the wavelength here is similar to the size of the gap, and the wave is going in this direction. As it goes through, the wavelength stays the same, but what we get then, oh, this is a poor diagram, I apologise. We then get the wave spreading out. Okay, so this is diffraction. Now, there's Huygens. I cannot say the name, and actually when I put out a thing with some other teachers, nobody could agree. I say Huygens, but I think it's a Dutch name, and actually it's not really pronounced like that. Huygens construction basically says if you imagine a wavefront, then you've got to imagine lots of little wavefronts along that, and basically every point in that wavelength every point in that wavefront is a point from which other waves can come out. So basically, if you think about this point here, there's going to be some other waves that come out, and it's where they cross over and they all kind of start to interfere. That's where the next wavefront appears to be. Okay, and basically from here you've got like lots of waves coming out. Is that right? Hold on. I'm going to do it better. So imagine you've got a wavefront, and we think about a point here. That's going to then emit more wavelengths like this, and there's going to be a point over here that emits more. And basically, where these all kind of sort of interfere is where the next wavefront is. This is actually really hard to do live. I probably should have. Yeah, I've got some pre-recorded videos. Then from this point here, you have the next wavefront, and then that's like our secondary source of wavelets, and where they all kind of interfere is where the next one is, and so on. Okay, that's badly explained. People have said actually in the chat that longer waves diffract more than shorter waves. Basically, you get the maximum diffraction when the wavelength is equal to the aperture. Okay, and that's why light, which has a short wavelength, will only diffract when you have a very, very small aperture, like a diffraction grating, whereas sound, which has a much longer wavelength of about 1 meter, will diffract around an open door. Okay, yeah, so then you need to think about if you sent light through maybe a double slit, then what we have then, do you have double slits? No, okay, let's use a diffraction grating. Okay, so imagine we had this thing here, but we had lots and lots of small apertures. And what we can then do is we can send a wave of light through it, like this. So this is maybe some coherent light source, maybe from a laser or something. At each of these points here, as it passes through, it's going to diffract, like this. And what you'll see is there's going to be lots of parts of interference of those waves. Now that means there's going to be lots and lots of destructive interference where we get basically nothing. But what we do is if we were to maybe look on a screen somewhere over here, what we see is a really kind of bright spot here. There'd be a big gap and then another bright spot and another bright spot and so on. Now, what we can do is we can basically look at n, which is the order of the bright spots. Now here we've got the 0th order, we then got the 1st order to each side, and then we'd have the 2nd order, and so on. Okay, so I'm just going to extend the screen. You can see why I've done a lot more kind of pre-recorded videos, which has everything kind of all recorded nicely, so the mistakes get edited out. And basically, if we were to follow this back, you'd find that there's like a bright spot all the way along here, and all the way along here, and all the way along there, and all the way along there, and all the way along there as well. Okay, so we've got n, we've got the angle theta, and theta is the angle in here. Okay, so that's theta. We have the wavelength of the waves, and also we have d. And d is going to be the number of, it's going to be the distance between the diffraction grating holes. Okay, okay. So just looking at some questions, Jack says, to be fair, okay, yeah, so I see what you mean, Jack, about longer. Yeah, so we'll come on to this thing about how, at the moment we've got monochromatic light, so all of the, we just get these spots here. If you send white light through a diffraction grating, we find that the amount of diffraction of different colours does depend on the wavelength. So yeah, maybe that is quite true. Okay, so we know that for a diffraction grating, n lambda is equal to d sine theta. Okay, so this is going to be the order, that's the wavelength. We've got the spacing between the diffraction gratings, and also we've got sine theta, and it's this angle theta that you actually don't measure directly. Instead, you might measure the length over here. So to work out theta, we know that sine, you can basically work out this length, or the distance to the screen, and also you can look at the distance between the central part and this point over here. But of course, you don't just want to measure that directly, you want to measure from here to here and divide by 2. And of course, we then know that tan theta is equal to the opposite side, which let's call it x, divided by L. So you don't necessarily measure theta directly, but you might measure x and L using a meter ruler, and then use that to find your value of theta. Now, a good point there about white light. If you have white light, we can see that if we've got the same order, and we've got the same diffraction grating, then the wavelength is going to be proportional to sine theta. Now what that means is if you have a longer wavelength, that's going to make sine theta bigger. So I'm just deleting some people out of the chat. And therefore different colours diffract by different amounts. So if you put white light through, you'll get a white central point, and then you'll have like a rainbow that's kind of like red all the way through to violet on each side. Okay, where are we? Of course, most of the time, what we can actually do is use this thing here, and this is now Core Practical 8. And what we can then do is we can use this setup with the diffraction grating to measure the value of lambda. Okay, so lambda is going to be equal to d sine theta over n. Okay, and basically what you can do is you can maybe either use a travelling microscope to measure the diffraction grating spacing, or you just find out what that is. So that just might be your bit of given information. You can work out the value of theta from measurements of x, the distance between the fringes and the distance to the screen. And also you can measure, or just work out which of these we're looking at. Is it the first, second or third order? And if you do that, that then allows you to work out the wavelength of light just from some macroscopic kind of measurements. OCRA I'm going to be doing tomorrow. That's the plan. Does that help? Okay. So Luke, the closer, yeah, so basically the closer the wavelength of light to the size of the diffraction grating, the more it diffracts. Yeah. As a ratio of the wavelength to the diffraction grating increases towards 1, sine theta tends towards 90 degrees, so the angle of diffraction is larger. Yeah, so there will be a point that, yeah, I don't know how to answer that really. Yeah, generally, Luke, I think that as the wavelength gets bigger, yeah, I don't know the answer, I'm afraid. Sorry, Luke, about answering your question. Sorry about that. But generally, what you can do is you can look at the number of orders of light that you get, and how that's related to the value of lambda and sine theta. But I think basically you get most diffraction, where you get the most diffraction through the aperture when the lambda is equal to d. Does that make sense? Sorry. Okay. Right. Okay. Right. Let's do the next bit, which is about the wave. Oh, this is like kind of quantum stuff. This is good. Okay. So electrons. Basically, the way I see it is they travel as a wave, and they interact. I spelled that wrong, I think. Interact like a particle. Okay, so that means they have both wave and particle-like properties, and that means we have this kind of wave-particle duality. Okay, and basically what you can do is you can get a Teltron tube that looks a bit like this. Over here we have something, and what we do is if we have an electron gun which uses thermionic emission, so basically we can boil some electrons from some metal. The electrons shoot away from that. They're in this kind of evacuated glass tube, so it's a vacuum. We send them through maybe a piece of graphite. Now the thin piece of graphite, because it's got this crystalline structure that you remember from GCSE chemistry, it's got these kind of regular layers, that acts like a diffraction grating, but it diffracts like this way and this way and this way and this way. It's like a 360 degrees diffraction grating, and that means we then see, rather than like just a central maxima, we see like a central bright ring, and then we have rings around it. Okay, and this is where we have electron diffraction. I did a video a couple of weeks ago where looking at, I think, 5 different types of Teltron tube, and that showed a video where this is. Basically, electron diffraction, we can only see this pattern because electrons must travel like a wave, and as they go through this thin sheet of graphite, which has a spacing similar to like the wavelength of these electrons, we get this diffraction pattern occurring. Now the wavelength is equal to h over p. Okay, the wavelength of those particles is equal to Planck's constant divided by the momentum. So it's often also written as lambda is equal to h over mv. Now, of course, we know the mass of electrons. We can work out their velocity, because their velocity is going to depend on their kinetic energy, and that's going to depend upon the charge on the electron and the potential differences accelerated through. So, for example, if we knew that we accelerated this to 100 kilovolts, that means all the electrons would have 100 kilo electron volts of energy. And if we know the energy they've gained, we can work out their kinetic energy, which allows us to work out their velocity. And of course, we know Planck's constant, therefore we can work out the wavelength of those electrons, for example. Yeah. So, right, I'm just seeing what else it says. Waves can be transmitted and reflected at an interface between media. I guess that just means that a wave will kind of like be reflected back, or it can be absorbed by material. Okay, pulse echo. So I guess pulse echo is about ultrasound. And basically you might have something which emits waves and also detects it. And basically this wave might get sent out. It might reflect off an object, so it could be something inside a person, it could be a defect in material, it could be a shoal of fish under the sea, and basically that's going to send it back again. And what we can then do is we can look at the time that something travels for. We know how quickly it moves through that medium, and therefore we can work out the distance that that wave has travelled. But of course, what we have here is the fact that that's our distance, s, from here to the object, and that means in the time it takes to go there and back again, there's going to be the distance travelled is going to be equal to 2s. Okay, AQA should be on Saturday morning. That's the plan. So yeah, Saturday morning we'll do some AQA stuff. Right. We then have some information about EM radiation, how it's, the photon model and how these developed over time. Yeah, so the next bit, I guess, is again, I'd say the specification kind of messes stuff up a little bit in terms of like the way it's done, but basically, EM waves, we often think of them as a wave. But there's also a particle-like nature to them, which is what we call a photon, and the energy of that wave is equal to hf. Okay, so effectively we've got the photon-like property, so the energy of that photon is related to the wave-like property of that. So there we go. So E equals hf, and effectively, if you think about the EM spectrum, you've got radio, micro, infrared, visible, ultraviolet, X-ray, and then gamma. Okay, what we find is that when you've got a high frequency over here, that's where we have more energy in those waves. So that's why we have things like ultraviolet, gamma, and X-ray are the ionizing radiation because they've got enough energy to ionize atoms. Right, people are asking, I probably should put this in the chat again. I'll do... Sorry, hold on. Okay, I'm just going to pin that message so people can see that we're going to be doing some OCR and AQA stuff as well. Did that pin? Yeah, cool. So yeah, basically the higher the frequency, the higher the energy carried by the photons in that. We then have the photoelectric effect. And I think people often find it really difficult to explain the photoelectric effect. The way I see it is like this kind of energy well, where you've got basically like an electron that's kind of on the surface of a metal. I think it's quite important to say that. So that's maybe on the surface of a metal. And basically we need to have enough energy to get that out and actually liberate it from that surface. Now, if you've got a photon that comes in, if that photon has enough energy, or more energy than this energy needed to get that out of that kind of hole, hole's the right word to say that, then, and that's obviously going to be equal to hf, this energy here to liberate an electron from the surface is what we call the work function phi. And basically, if this energy here is bigger than that, then the electron can get to the surface, and any extra energy will be in the form of the kinetic energy of that photoelectron. Okay, so the energy of the photon that's incident on it is equal to hf, and that's equal to the energy required to liberate it from the surface, the work function, and any extra energy is then the kinetic energy of that liberated photoelectron. So therefore, that's equal to a half mv max squared. Okay. Now, not all of the electrons will have this amount of energy, but that's the maximum they could possibly have. People are asking some questions. So, how's this going to go on for? I don't know. I think I'm about 3 pages in. I've got maybe 1, 2, 3, 4. Oh, it's going to go on for, I reckon, another couple of hours. Something like that. So it's maybe 2 o'clock now. I reckon we'll probably go to maybe 4 o'clock. I've got my milky tea. I've got everything I need. We're just going to keep going and going and going. So yeah, basically I'm just going to cover all of the main topics that come up for Edexcel Paper 2. I'm going to do OCR on Thursday and AQA on Saturday. That's my plan. And what you can do is, if you want to find out, I'm just going to put a link here to my yeah, basically, if you go to this page, I'm just going to put a link up now. Then, if you go to that page, which is physicsonline.com, and you sign up at the bottom to my newsletter, then I will include information in that newsletter about what's coming up and where you can find the links to these live streams. Okay, so basically, if everybody now goes to physicsonline.com, or maybe do it afterwards, you can find a link to my newsletter, and then I'll email out the newsletter list with the timings for OCR, timings for AQA, and also links to where you can find everything. So Luke, it will be saved, both on YouTube, it's always up there, and also it'll be on my website as well. So I'll put links on A-levelphysicsonline.com. Okay, right, that's the photoelectric effect. What next? I think it's pretty much it, really, isn't it? Yeah, and it's about not necessarily the photon interacting with the electrons within the actual atom and like having like the electrons jumping from one shell to another. This is about on the surface of that metal. Okay, right. Okay, let's move on to the next bit, which is, the photoelectric effect does provide evidence for the particle nature of electromagnetic radiation. So the evidence that we've got photons is that basically one photon can liberate one electron. Okay, and the other thing is that if you had a wave-like property of light, then this electron would absorb some energy from one bit of light, and if you increase the intensity of that radiation, then there'd be more energy being absorbed per second, so more photoelectrons would be emitted. However, what we found by experimentation was that if you increase the intensity, then that means we have more electrons being emitted. So there's basically a link between the amount of energy per second landing and the electrons per second leaving. But also there's going to be this threshold frequency below which no photoelectrons are emitted. And it's only when you go above a certain threshold frequency, F0, that we have enough energy in that photon, because the energy is equal to HF0, and it's only then that this is going to be equal to the work function of that material. Beneath this frequency, there's going to be no photoelectrons emitted, even if it's really intense radiation. And that gives, again, a bit of evidence about the particle-like nature of light. Okay. Okay, right. We then have the next bit, which I think is quite nice. We have this kind of diagram. We've basically got the ground state down here. We've got like surface of the thing there. And what you need to know about is the energy absorbed or the energy emitted, okay, as electrons go from one level to another. Often we might have energy in joules, or we have energy in electron volts, where 1 electron volt is the energy gained by an electron accelerated through a PD of 1 volt, which is 1.60 times 10 to the minus 19 joules. And of course down here we often have negative values of energy, because if an electron gains energy, eventually it gets to a point where it has 0 energy as it's liberated and ionized. Okay, so what we can see here is that either the energy absorbed has to be a discrete level of energy, because we have a discrete level of energy between these shells, the fixed shells or fixed energy levels where electrons can be. Okay, and again, this one here, you're going to rely on the equation that says E is equal to HF. Right, so I think that's kind of like the last bit looking at waves. Right, how's everybody getting on, by the way? We're going to go on to the next section in a second. I'm just going to pour myself some more milky tea before we go on to thermodynamics. Try not to get too many splashes everywhere. So again, this is all about Edexcel Paper 2. A kind of a whistle-stop tour, just like a summary of every single bit of the paper. The next thing we're going to be looking at is thermodynamics, and then we're going to be looking at space, nuclear radiation, gravitational fields, and then finally some oscillations. Answering people's questions here. AQA Paper 2 I'm going to do Saturday. Will a live stream be saved? Yeah, I'll save it on YouTube, and also I'll put it onto my website, which is A-levelphysicsonline.com. By the way, if anybody likes this, don't forget you can like the stream. That's often a nice thing to do. I think YouTube likes that. And of course, yeah, it's good to know that people are actually watching. So let's just see some more comments. Yeah, Jack, there's not as many things for Edexcel. It's basically because About 50% of people do AQA, about 30% do OCRA, and about 10 to 15 do Edexcel. Am I going to do materials as well, Luke? Good question. Yeah, I did materials already. That was in the first stream that then for some reason stopped. So yeah, materials is in like the part 1 of this. So I've done all that. So I've done all that earlier, but you can obviously go ahead and watch it afterwards. Okay. Right, so just seeing what we're going to do next. So thermodynamics. Again, if you want to watch any videos about anything that comes up here, then I do have loads of stuff over at alevelphysicsonline.com. Right, the first one I'm going to do is, so this is thermo. Now the first part really is the same as GCSE. Okay. Okay, so maybe we've got our temperature up this axis, we've got the energy or the internal energy along that axis. Okay, here we've got a solid, liquid, and a gas, and of course we've got our phase changes. Things are melting or evaporating and turning into a vapor. Now, the two things that we can think about for this is that the change in energy supplied is equal to mc delta theta, and that's where we've got something where it stays in the same state. So we might, for example, look at the change in energy supply, or the energy supplied is equal to mc delta theta. Little c is our specific heat capacity. Delta theta is our change in temperature. So this is the kind of thing we can think about at these parts of the graph. Okay. The other one, which I'm going to do in purple, is that if we're looking at the energy supplied for a phase change, it's equal to this. Okay, so this could be the specific latent heat of vaporization or the specific latent heat of fusion. And we can see at these regions, if you've got a pure substance, it changes state at a constant temperature, and that's why there's no delta theta there. I don't really know why there's a delta M there, because surely the mass stays the same. So yeah, L is going to be our specific latent heat, sometimes of fusion, if you've got a solid to a liquid, or it could be the latent heat of vaporization from a gas, from a liquid to a gas. Okay, now I would say that that's no different to what you'll have done at GCSE beforehand. So that's kind of all good stuff. Core Practical 12 is calibrate a thermistor and a potential divider circuit as a thermostat. Okay, so again, this practical, number 12, is actually testing your ability to look at a potential divider circuit. So that's simply where you've got a power source, you've got a resistor, and also you've got a thermistor. Okay, and that's all the potential divider circuit is. Yeah, so basically that's our potential divider circuit. Now if you're going to calibrate this, what you can use, and again there's loads of different variations, each school might have different equipment, but what you might have here is you might have maybe a variable resistor, and you might be measuring the potential difference either across this or across this thing over here. Now if you were to put this into some water, again you've got to remember about how the resistance changes with temperature. You get a graph for a thermistor that looks a bit like this. Okay, now if you know the temperature, then that means you can know the resistance at a certain point, and you can work out the resistance of this. We might balance it. I don't know, there's so many different ways of doing this. There's not like one simple way of doing it. But basically, if you know the resistance of this, it might give you an indication of the temperature. Okay. Now you could work out the resistance of this particular component, because what you could do is you could measure it. Maybe you can look at the current going through it. You could look at the potential difference across it, and that would allow you to calculate its resistance at a certain point. And if you know its resistance, you can then work out the temperature at that particular point. And of course, to calibrate it, you maybe have some certain things. So maybe you know that the temperature is equal to 10 degrees. You could work out your value of resistance. You could then maybe set your temperature to be maybe 20 degrees. You then measure your resistance there. And if you know the resistance at this and the resistance at this, if you worked out the resistance at another point, that would then tell you what the temperature is. So this is just like an electronic thermometer, it's a thermostat. But again, there are so many different variations, and don't forget everything you learnt in paper 1 about electricity, because that's going to be useful when it comes to this one over here. For number 13, for the core practical 13, this is about the specific latent heat of a phase change. Okay, one that's often done is stearic acid, but again, what you might get is a graph of data, and you might have a cooling curve that looks something a bit like this. Okay, so you might have your temperature with time, potentially, and it's basically looking at the time it takes at a certain rate of energy transfer for maybe something to change as it's melting. Often it's a bit more controlled if you're putting the energy in, and you might have maybe something that you sort of heat up. I suppose actually, if you're going to heat something up, this is why I like pre-recording videos, because all my mistakes get edited out. You might heat something up, you get a great rate of heat transfer, then it kind of plateaus towards the phase change, and then once it's all phase changed, you then get something like this. Okay, and it might be in this region over here where we know that we've got no change in temperature, and we know the time that occurs for, and if you maybe know the power of the energy supply and the time it's on for, that allows you to work out the energy transferred. And of course, if you know the energy transferred and you know the mass of something, that allows you to work out the specific latent heat of fusion or of vaporization. It could also be the change. Yeah, so I think that could be it potentially. Right. Okay. We then need to think about this internal energy. Sometimes it's given us the letter Q, and basically this is equal to the sum of the kinetic energies plus the sum of the potential energies of all the particles within the system. Okay, so they're going to have some kinetic energy, which is how fast they're kind of moving, and it could be jiggling around the same position, or it could be rotating, but there's this kind of kinetic energy, which is often related to the temperature. And also the potential energy is going to increase as you add energy to something and it breaks apart the bonds between the bits. Again, that's just a GCSE definition. Right, let's go on to another page. We're now going to talk about the difference between Kelvin and degrees Celsius. Okay, now the Kelvin scale is basically fixed at 2 points. There's going to be the minimum internal energy, and that's at 0 Kelvin. And there's also the triple point of water, which we call 273.16 Kelvin. Okay, so this is absolute zero. And this is the triple point of water. Now, the reason that those 2 points are used is that on a phase diagram, which looks a bit like this, and I think we've got like pressure and volume. Is that right? No, it's pressure and temperature. There's basically one particular temperature at one particular pressure where water can exist as a solid, a liquid, and a gas. I think that's the right way around, but basically there's a thing called a triple point where at the same temperature we can have liquid water, ice, and water vapor, so gas. And basically they're the things that define the Kelvin scale, and there's basically 273.16, I think, was it 15? 273.16 bits between it, and each of those is equal to 1 Kelvin. Now, of course, if we add, we can kind of go up the scale even more, and that's when we get to the Celsius scale, which is basically saying that at 273.16 Kelvin, that's equal to 0 degrees Celsius, and 1 Kelvin is equal to 1 degree Celsius. So that means 373.16 Kelvin is equal to 100 degrees Celsius. Okay, and that is the Celsius scale. It is not the centigrade scale, which was based on the olden way of saying that 0 degrees centigrade is where water freezes and 100 degrees centigrade is where water boils, because that didn't take into account the fact that at different pressures, water boils at different temperatures. Okay, so that's about the absolute thermodynamic scale and this one here. I would say that this one here is often given the symbol theta. This one is given the symbol T. Okay, and what you want to be doing is when we're looking at ideal gases in particular, we always convert temperatures into the Kelvin absolute number. Okay, that making sense? Is anybody still watching this, or has everybody gone and done their own revision? Yeah, right. So again, do let me know every so often in the chat if this is useful. Do click the heart button to let me know that actually people are watching this, and if you haven't already done so, do make sure that you like the video. I think YouTube like all of that good stuff. Okay, the next equation then is about PV is equal to a third NMC squared. Okay, yes, people are still watching. Good. Luke, Jack, great to see people are still watching this. Okay, so the next one is this. Okay, now the derivation for this, I've actually got a whole derivation booklet. You can find this at A-level physics online, and basically you can download all of these derivations. Now what I did previously was I've got my derivations for the parts of the course to do with the ideal gas equation and stuff like that. So what have we got? Do I have this one? Yes. So Ken, good, this is useful, right. So basically, if you have, I'm just going to do it on this, and basically if you want to, if I just zoom out slightly, if you want to see the derivation, then I'm going to leave it here now, and you can just come back to this part of the thing, or just screenshot it. If you've got a particle of mass m moving at v in a cubic container of side L, when it impacts the side and bounces back again, there must be a force provided by the outer wall S. That's a bit of Newton's third law. And the change in momentum is going to be its initial speed, which is mv, minus its initial momentum mv, minus its final momentum, which is m minus v, because it's an elastic collision. And therefore the change in momentum is 2mv, and the force is going to be equal to the change in momentum divided by the time. Now the time between collisions, if it's going through a distance of 2l at a speed v, the time between collisions is 2l over v, and therefore the force is equal to 2mv over 2l over v, which is mv squared over L. But that's just in the x direction, of which there are n molecules. But of course there's going to be the x and y direction as well. Sorry, there's going to be the y and the z, so there's going to be 3 dimensions. And there's going to be a whole number of particles going left and right. And therefore, if we think about the pressure on just one face, it's equal to the number of particles over that area, which is going to be equal to this force times the number of particles divided by the area, which is L squared. And you've got 1 over L here, so that's going to come over L cubed, which is V. So the pressure on one face is nmc bar squared over V, but of course there's going to be n particles in 3 directions. The number of particles in one direction is going to be a third of this big N, and therefore P is equal to nmc squared over 3V, or PV equals a third nmc squared. Now, you need to be able to derive that for Edexcel. Now, I would say that Ken, is this derivation necessary knowledge? Yes, it is. And I suspect in an exam they wouldn't ask you to derive it from scratch, but they might ask you to derive part of it. So this is something that you need to know. If you want to download this to revise, rather than trying to copy it down now, you can find this on my A-level website. I'll put a link up beneath the video once the live stream is finished as well. Okay, so you can find this derivation booklet, and you can download all of these derivations that you might need to know for A-level physics. Okay, so you need to know that. And this is for an ideal gas. The next one is about the relationship between pressure and volume of a gas at a fixed temperature. And basically, when you do a practical, this is now core practical 14, you might have a large cylinder of gas, and basically there's a plunger at one end. You can basically measure the volume, and you can measure the pressure, because on the side of this you have some kind of pressure gauge. Okay, and you want to make sure that as you compress the gas, you do it really, really slowly so it stays at a constant temperature. So when we do that, if we look at the pressure and the volume, we get a relationship that looks like this. Basically, at a lower volume, we have a higher pressure, or a larger volume, we have a lower pressure. Now that doesn't really show us much, so a better way of doing it is maybe having P and 1 over V, and then you get this relationship here. And that means we can say that P is proportional to 1 over V, or PV is equal to a constant. Now again, a lot of you, if you did triple science, will have done that at GCSE. And so the pressure times the volume for an ideal gas is constant, provided it's at a constant temperature. Now actually, does it have what that's equal to? Yeah, and in actual fact the constant is equal to nKT. Okay, so the pressure times the volume is equal to the number of particles times the Boltzmann's constant times the temperature, the absolute thermodynamic temperature of that gas. And this is the ideal gas equation, or one of them. But Edexcel don't use PV equals nRT, so there we go. We also have the equation that says you have to, and basically you have to be able to derive this. Now the other thing that you have to be able to derive is a half mc squared is equal to 3 over 2 kT. Okay. What time will I be doing AQA on Saturday? I don't know. Probably maybe a similar time, so like kind of mid-afternoon if that works. So it's not too early but not too late. And also it gives you plenty of time to catch up on Sunday, Monday, Tuesday, Wednesday. Okay, so probably midday on Saturday is probably when I'm going to do it. Okay, do you need to know the derivation for AQA? I'm not quite sure. Okay, now to derive this one over here, we basically say that this thing here is equal to this thing over here. Is that right? So again, in my derivation booklet, let's have a look. Yeah. So for this one, we know that PV equals a third nmc squared and PV equals nKT, which is basically this equation and this equation. If we equate the two things together, we can say that a third nmc squared is equal to a nKT. So let's just do that. So basically what we can say here is PV is equal to a third nmc squared, and that's equal to nKT. We can see that the n's cancel, and therefore we can say that a third m times c squared is equal to kt. Okay, now if we multiply both sides by 3, we can say that m c squared is equal to 3 kt, and now if we divide both sides by 2, we can say that a half m c squared is equal to 3 over 2 kt. And of course a half mc squared is just going to be the kinetic energy of any individual particle, and that means that we can say that the kinetic energy of one of the particles is related to 3 over 2 kt, or the kinetic energy of a particle is proportional to the temperature. So the kinetic energy of the particles really tells us about the temperature of the ideal gas. Okay, and yes, I will be doing OCR on Thursday. Okay, again, that's another derivation you need to know, so you can screenshot this now or catch up and download this whole derivation booklet from my website. Right, we then have something about black body radiation, and I think there's a couple of things here. So often when you've got black body radiation, what we have is a kind of graph that kind of looks a bit like this. And as you go to hotter things, it's not the best graph, is it? Basically, what you have along here is maybe the wavelength along here, and then we've got the amount of radiation being emitted. So that could be maybe the intensity of radiation. And effectively, when you've got a shorter wavelength, as you go to a shorter wavelength, we get a peak which is more intense, and there's going to be a greater area underneath that curve. The two things you need to know about, and this is often related to questions about stars, is that the luminosity is equal to the Stefan's constant times the area times t to the 4, and also the theta max times t is equal to 2.898. I'm just times 10 to the 3. Okay, and the units for this are mK. So that's not millikelvin. It is it is meter Kelvin. Okay, does that help? Hopefully a little bit. So basically this is like the kind of ideal kind of like black body curve, and it's basically looking at how this peak wavelength, theta max, basically as you have something which is hotter, it goes from like the infrared, because everything's emitting infrared, and it goes into the visible part of the spectrum, and as we get something even hotter, then it's going to go into like the ultraviolet region where we have our kind of lambda max, and also the area under the curve gets bigger because it's emitting more energy per second. Okay, is that good? Right, I think that's basically thermodynamics done really quickly. I need to do some kind of proper videos on these where I can go into it in a bit more detail and like actually edit out all of my random chat. But yeah, hopefully that's helping so far. Right, the next thing is we're going to be looking at some stuff to do with space. I'm just going to top up my milky tea. So there's some in there. Here we go. For anybody who's coming in to see my live streams next week, you might have seen I've been increasing the amount of Lego I've got. I do have some more Lego boxes to open. So if you're back in the evening streams after half term, I will be opening more Lego as we improve my collection of my huge amount of just Lego, which I suppose I'll be using in videos in the future. But I've actually not used any Lego at all today. Okay, right. Where are we? So, space. The first one is about, I'm just going to put space up here. The first one is about the equation that relates the intensity to the luminosity of a star over 4 pi d squared. Okay, now this is kind of obvious, isn't it? Basically, if you've got something which is more luminous, then it's going to be giving out more energy per second. So the intensity of that is going to increase. And of course, the luminosity is what we just worked out in that previous thing about being related to pi times... Oh, I've just lost my bit of paper. It's related to pi times the area, kind of t to the 4. Okay, it's also going to be related, or in actual fact, the intensity is going to be proportional to 1 over d squared, or sometimes we call it this 1 over r squared relationship, where d is just a distance to that star. And basically, this says that if you go twice as far away, that the area that energy spread over is going to go up by a factor of 4, and if you go 3 times as far away, it goes up by a factor of 9. So you've got the intensity proportional to 1 over d squared, and that's kind of brought together in this thing over here. Okay, now the way that we actually measure, and this is, by the way, am I doing another live stream for Edexcel, Jack? No, this is just going to be one big live stream for Edexcel today. So I'm just going to do Edexcel today, but I will include all that information in the newsletter when I send one out later, and I'll put links to it for anybody who missed it, and basically have all the information there. So that's the plan. So that's the intensity of a star. Now, a long time ago, it was very difficult to actually measure how far stars are away, but what they used was parallax, where basically things a long way away appear to be fixed, and stars which are a bit closer would vary their position throughout the year. Now, the way that I sort of can really demonstrate this, it's quite hard to do, but if you put your one arm out a long way away and you put your other finger kind of closer, and if you look at that finger through your left and your right eye, you will see that your fingers which are a long way away tend to be relatively steady in their position, but the closest finger changes position depending if you're looking through your left or your right eye. And that's a way that we could measure the distance using parallax. Okay, and basically you had the sun, and you had the Earth in maybe the summer and the Earth in the winter. A long way away, you had the kind of fixed stars that were so far away they didn't appear to change in position. But when you had stars which were much closer, like this one over here, in the summer, when you looked at it, it would appear to be over here. And when you looked at it 6 months later, it would appear to be here compared to the things which are a long way away. Now the distance between, or the mean distance between the sun and the Earth is 1 astronomical unit, I think 1.5 times 10 to the 11 meters or something. And of course we wanted to measure the distance out there. Now we did that, effectively you want to know this angle here, which is kind of like this angle in here. And basically, when you've got theta being equal to 1 second of arc, and that's equal to 1 over 3,600 degrees, then the distance d is equal to 1 per second of arc, which is equal to 1 parsec. Okay. Adrian, yes, you should do Physics A-Level next year. It is a great course to be doing. I definitely recommend it. I'm a bit biased, but I think it's really interesting. And this is where it gets interesting, looking at space and stuff like that. Now, this one over here is a way that we can measure things which are relatively close to us. So this kind of, I guess, our galactic neighbourhood, this is like stars which are quite close. How do you measure the distance to things over here? Well, basically what we need to look at is we need to look at standard candles. Now, a standard candle is an object where it's an object of known brightness. Now, basically, what we can look at is how bright something appears to be, and if we know how bright it actually is, we can then work out the distance to that. And basically what we have is our apparent magnitude, and that's how bright it appears. And there's also its absolute magnitude. Now, to be honest, the Edexcel specification doesn't go into a huge amount of detail. And this is basically how bright it really is. Okay, so a standard candle could be maybe some kind of supernova. Often we have stars which actually oscillate in brightness, and the brightness depends on the time it takes for them to go dimmer and brighter. Okay, so what we have are certain stars where over time, if we look at their brightness, it kind of does something like this. Okay, and if we know the time for a cycle, that time for a cycle of it getting brighter and darker, that's actually related directly to its absolute magnitude, which I think is capital M. And then we can then actually look at these stars and go, okay, we can see that that's maybe 27.2 days for it to go through a cycle of getting brighter and dimmer and brighter and dimmer. If we know it's exactly 27.3 days, we can look up at the chart and go, well, actually, that must be exactly this absolute magnitude of brightness. It appears to be this bright, and therefore we know how far away it is. And I think that we, again, there's not much information in detail given to you in the specification, but I think they could give you some data and ask you to use that data to actually work out how bright things are, and they might introduce an equation, maybe using m over m and like a log to the base 10 kind of thing. So again, the equation's not actually given to you in the Edexcel specification, so I don't think you need to go into too much information about that. But basically, it's a bit like if you look at car lights and you see headlights from a car but they're quite dim, you know that close up those car headlights are really bright, but if they appear to be dim, then that means you know the car is quite a long way away. Whereas if you had another car that had equally bright headlights but they appeared brighter, you know that that car is closer. Would they ever ask you how to determine the distance to a star using a standard candle? No, I think it's just understand, and therefore I think it would be a kind of question where they might give you some data and you have to interpret that data and describe how that data could then be used to interpret the distance. So I don't think it would be just a how would you do this. It would be like interpret some data that they've given you about something. So that's just a case of reacting to the question. Okay, the next one is the Hertzsprung-Russell diagram. Okay, it looks a bit like this for the main sequence. So these are the stars which are in a stable phase. Our sun is somewhere down here. We also have stars which are quite dull, but they give out lots of light. So maybe we have our luminosity along here. And we maybe have our temperature going this way. Okay, so what you might find is that you get stars which appear to be blue and kind of purple around here. And then as you go down, you then get like the yellowy stars. I don't have a yellow pen, so that will have to do. And then you get like your reddy stars kind of down here. Okay. Now you also get some things up here which have a low temperature, but they give out lots of light. So these are our red giants or red supergiants. And also you might get something which is very luminous, which isn't very luminous. It doesn't give out much light, but it's really quite hot. And this is where you might get your white dwarf. Okay, yeah. So this is a Hertzsprung-Russell diagram, HR diagram, and basically we can use it to look at where a star sits if it's in the main sequence, and then as time goes on it would move up to the red giant phase and maybe back down to the white dwarf phase. Okay, so that you can sketch it, you can interpret it, and it relates stellar luminosity to the surface temperature. Okay, again, not too much information about that. Of course, you do need to be aware about the fact that, and again, if you've done triple science, you know about the life cycle of stars. They kind of start out in a nebula, they come together in this protostar, you know, have a main sequence for most of its life. And as we start to run out of fuel, and then we start to fuse heavier elements, that's when the outer part swells up, but it gets cooler at the outer sides. And then it'll either shrink and die as a red dwarf and then a black dwarf, or if it's really supermassive, it might explode into a supernova. Okay, right. So if you're taking OCRB, Veram, I would say, I'm just going to put a link that if you go there, you can find, I'd say, a couple of resources that might help you. I know it's my own website, but I do have stuff there for OCRB, including, I think, all of the content, like even like the digital bits and pieces and things like time and motion and stuff like that. So I'm just going to put a link up here. There we go. So that's some stuff to help with OCRB. Hopefully that helps. Okay, so that's an HR diagram. The next thing is we have the Doppler effect, and basically the Doppler shift is going to be equal to the change in frequency over the original frequency of the light being emitted, which of course is going to be pretty much the same as a change in wavelength over the original wavelength, which is equal to the speed of recession, often of that galaxy or that star, over the speed of light. Okay, so I don't think we really need the words dead much. Basically, if we know the change in wavelength, what we actually find is that light which is emitted at maybe a shorter wavelength, because space is expanding, then actually as space is getting bigger, that wavelength is going to extend towards the red end of the spectrum, and therefore what we often have is redshift. Okay, and it's often the light that we see in the emission or absorption spectra that is actually shifted. So you might get the certain spectral lines, and basically these spectral lines tend to be shifted, and also they kind of stretch. That as all of that light is shifted, often the pattern gets pulled apart slightly as well, and it goes towards the red end of the spectrum. Okay, so you need to know about that and about the change in wavelength or the change in frequency of that light and how that's related to the recessional speed of that light, or the recessional speed of the galaxy that's emitting the light to the speed of light. Okay, and of course, if we look at this on a graph where we look at the recessional speed and the distance, we get something like this, okay, where V over D, the gradient of that line, is Hubble's constant, h naught. Okay, and basically this says that as things are further away from us, so galaxies often which are further away, they have a greater recessional velocity on average. Of course, there's going to be some variation around that, and there might even be some local galaxies which are slightly moving towards us. But basically, the pattern is that everything is moving away from everything else. V over D is equal to h naught, and because that's effectively meters per second, or you could give that in meters per second, you divide that by meters. That means Hubble's constant has the units of seconds to the -1, and therefore roughly 1 over Hubble's constant will give us the age of the universe. Of course, the difficulty is it's very difficult to actually measure Hubble's constant exactly, and of course this is assuming that everything's been accelerating at the same rate. However, yeah, at the moment, and this is kind of like the last statement here, is that we don't exactly know what's going to happen to the universe. It hasn't always been extending or expanding at the same rate. It's actually been accelerating, and we think that it might be that there's this dark matter or even dark energy which is fueling the accelerated expansion of the universe. Okay, so that's, I reckon, space. We now have, how many more topics? We've got nuclear, gravitational and oscillation. So 3 more topics. If anybody has any questions in the chat, do you want to put them in now and I'll see if I can answer them. If anybody's got any kind of quick questions about stuff that we've covered so far. Okay. Okay. No questions so far. That means either everybody's happy or everybody's going to come back and watch it another time. Okay, so how does the density of the universe affect its fate? Good question. And also, Jamie, what time is the OCR revision session on Thursday? I'm probably going to start about 12 on Thursday. So about 12 o'clock, and then we'll just go on for however long it takes. So yeah, it might be like 2 or 3 hours. So my plan is tomorrow, bit of gym stuff in the morning, and then I'm going to do some more work in my new office, which will be amazing when it's done. And then, do you want to see a picture of my office actually? I'll just get up on my phone. So it's going to be like this, but it's going to be bigger. So if you're in year 12, then hopefully you'll see a lot more videos that are coming up soon. Okay, at the moment, my office is kind of, I mean, it doesn't really look that impressive, but basically I'm going to have like a bigger background, if you see that. So there's going to be like a load of Gratnals trays. I'm going to have like, it's going to look like the back of a science lab. And also there's even things built out of Lego. So like that door handle there is actually just made out of Lego. So there will be plenty of Lego in this office. And actually I think even underneath the cabinet, that's Lego down there. So there's going to be lots of, you know, quirky bits and pieces. Also, I'm going to show you, I'm really proud of these. I've painted, I got some science stools from a skip the other day. And here they are. So, oh, I was going to get this out. So this is my science stools. I've actually discovered that I'm quite good at painting galaxies. So I've got a couple of stools. These are much more comfy than the ones you get at school with like wooden tops. So I've covered the top. I actually made the wooden tops. Yeah, and also that's like some padded stuff there. And actually, if you look on the legs, they're actually painted like galaxies. So I've got like my kind of galaxy space theme here, and I've got 2 of them, so I can invite people down. So people like you know, Mr. Turnbull, if you want to come down for some stuff. If you're another physics teacher, especially YouTube physics teachers, it'd be great to have you. Z Physics, I'm sure, will be sat on this stool at some point, and I've got loads of people I want to invite down to do more stuff. Right. should we do the next bit? Okay, yeah. There will be an AQA chat as well. I'm going to do AQA on Saturday, probably 12 o'clock beginning. I think that seems like a good time, so we'll do it Saturday afternoon. So yeah, so Saturday will be an AQA one. Tomorrow, Thursday, will be OCRA, and then today it's just Edexcel. Okay, when do you use radians and when do you use degrees on a calculator, Zana? That is a great question. I would say it tends to be, if you're doing a question about mechanics and stuff like that, then you tend to use degrees. You only really ever use radians if it's a question about oscillations or waves, I'd have thought. But it's difficult. I think it really depends on the question. I'd say normally, for me personally, I prefer to use degrees because I can just imagine, I know what like 42 degrees looks like. I know what 72 degrees is. I can just imagine it. If somebody said, oh, it's about 2 radians, I'd be like having to think, okay, well, 2 is like less than pi, so that's probably about 70 degrees. So I prefer, if it's a mechanics question, just to always use degrees and only use radians if it's something to do with frequency or something like that. But I think normally the question guides you one way or the other. Right, the next one, nuclear radiation. Okay, so we've got, okay, this is, so I think Edexcel have missed a trick here. What they've said is that the change in energy is equal to c squared delta m. Okay, I think, although that's the way it's written in the specification, they should have just written the most famous equation like this, equals mc squared. Basically what we're saying here is that the change in energy is equal to the speed of light squared times the change in mass. Okay, so what we have here is our, it's often the binding energy. So this is the energy required to kind of sort of bring that nucleus together, or it could be the energy emitted. And then over here, what we have is our change in mass, which we often call the mass deficit. Okay, and basically this is why fusion and fission both release energy, and it's also why when you bring like the constituent parts of an atom together, like the protons and neutrons, the total mass of the nucleus isn't the same as the total mass of the individual protons and neutrons added together. Okay, and of course when you do questions like this, often they'll give you data to maybe 5 significant figures. If we're looking at that mass deficit, it's often the mass defect is often a really, really small change, and therefore often we need to use 5 significant figures to actually do our calculations. Now the other one is we've got our atomic mass unit, okay, which is a bit like, I can't remember the definition now, is it the average mass of all the nucleons in a carbon-12 atom? I can't remember actually the definition. Yeah. Okay, so you've got the atomic mass unit. That's given to you, I think, in your data book anyway. And that's something that you sometimes need to use, because often we'll be given things in atomic mass units, and then you need to convert from that into kilograms when you're actually using this equation over here to work out the amount of energy which has been either emitted or needed to kind of bring things together. We then have the fission and fusion thing, where you've got a curve that looks a bit like this. Okay, so what we have is the binding energy per nucleon, and down here we maybe have the mass number, or the number of protons. Is it mass number or number of protons? I was going to put mass. Okay, and basically things which are quite light tend to undergo fusion, and things which are heavier undergo fission. Okay, and the thing at the top is often iron. Okay, so iron's pretty stable, but basically if we're looking at something like helium added to helium, or hydrogen added to hydrogen to make helium, then these things, as they go from here to here, then it's going to increase the binding energy per nucleon, and that means energy is going to be emitted when these things are brought together. Or when you split up something really heavy, then some of that mass is transferred to energy. Okay, so you've got fission of heavy elements and fusion of lighter elements, and you need to be aware of that. I probably could explain that better if I think I have explained it better over A-level physics online. Okay, then we've got fusion. The difficulty with fusion is that you've basically got a positive nucleus and you're trying to collide it with another positive nucleus. And in order to do that, you need to have really high temperatures because these need to have enough kinetic energy for them to get really close together. And also you want to have a high possibility or a high probability of them being actually collided together. And therefore you also need to have a high pressure. Okay, and that's why this happens in stars, in the dense kind of central part of that star where they're really, really hot. There's really high pressures of that kind of plasma, these kind of basically mostly just protons whizzing around. So it happens in stars, but it also happens in like test reactors. Okay, and the difficulty is that when you've got this plasma at a really high pressure and a high temperature, it's really quite unstable, and that means if it was to maybe touch the side of that, the walls of that fusion reactor, it kind of tends to lose its energy really quickly. So it works in stars, but it doesn't quite work in fusion reactors at the moment. However, fission is easier because what you have is something like maybe uranium-235. Okay, we add a neutron to that, it then becomes unstable, and then that uranium-236, it splits apart and it makes two daughter nuclei, and it releases maybe 2 or 3 extra neutrons, which can then go and react with another or be absorbed by another uranium-235, and that continues it. And what you need to know about is in a fission reactor, you need to have, what's it say? I think that's about all you need to know, really. But I think you need to know about fission reactors. Yeah. Now, in terms of nuclear fusion, what you don't have is 4 protons reacting together at the same time. What you might get is a hydrogen added to another hydrogen, and that makes deuterium. And then what later on you might get deuterium added to another hydrogen, which makes helium-3. And then it might be that you have helium-3 plus helium-3. Is that right? Oh yeah, sorry, helium-3 plus hydrogen-1. Anyway, whatever it is, there's often, I can't remember off the top of my head, basically you have a whole series of intermediate things. Is that right? So it's helium-3 plus helium-3 might make, oh, is that what it is? There's different ways of doing it that are done in stars and reactors. In reactors, you tend to react deuterium and tritium together. In stars, it tends to be a whole sequence of things. Yeah, I should probably have just revised that and learned off my head. But anyway, that stuff there they will give to you in the exam, and it's just a case of you looking at the equations that they give to you rather than remembering it, and actually be able to look at maybe the math defect each time. Okay, there is background radiation. And again, this is kind of like similar to what you did at GCSE. There's going to be several sources of it. It could be man-made from things like nuclear testing or medical uses of background radiation. There's also going to be natural background radiation from things like cosmic radiation from space. You've got radioactive rocks, which then decay and release radon. There might also just be radiation in things like your food and just the air and everything around us. So there's going to be background radiation. And you need to think about what you're doing if you're doing a practical. Maybe you look at the count rate and you look at maybe the counts per minute, and you maybe do this over several minutes or you do it multiple times, and then whatever the background reading is, you take that off the reading that you've taken for a radioactive source. Okay, so you need to know about background radiation and how to take account of it in calculations. You then need to know about alpha, beta and gamma, and I'm going to put beta minus and beta plus. So you need to know about what it is made out of. So 2 protons and 2 neutrons for alpha. You've got an electron or a positron, or it's just a photon for gamma. Okay, and therefore this is going to be highly ionizing. That's going to be ionizing, beta plus, as soon as this positron interacts with an electron, it annihilates, and that means it has a very, very short range. Gamma has a very, very long range. It can penetrate lots of things, but it's the least ionizing. So again, you need to know about alpha, beta, and gamma, and I would say beta minus and beta plus both need to be known about. So hopefully that's helping. You then have a practical. This isn't as neat as the first one I did about mechanics, is it? You then might have a practical about the absorption of gamma rays. So you might have your radioactive source here. So it's a triform there. Okay, so basically this is your gamma source. You then maybe look at background radiation, and what you could then do is you could increase the thickness of lead between the gamma source and your Geiger counter. Okay, you've got to take into account background radiation. You've got to maybe look at what this is when you don't have any of that, and then what you might find is that you get a graph that looks a bit like this. So if you've got a gamma source, you might well get a graph in the form of y equals e to the minus x. Okay, where basically we have this attenuation of the photons of gamma radiation, because it's not like if you double it, it kind of stops everything. So it might be that you have like 5 centimeters and it goes down by half. You put another 5 centimeters down and it goes down by half again. And it might then be that what you can do is you might take the natural log of some of that data to get a straight line to actually look at how effective that lead is at stopping that gamma radiation. Of course, safety is a big thing, so you need to make sure that you use long tongs to handle the sources so that you don't get contaminated and it reduces the radiation on you. You may need to make sure that you wash your hands afterwards, there's no eating in the lab, and all the kind of good standard stuff you've already done. We then have the spontaneous and random nature of nuclear decay. Again, if we look at either the number of particles or the activity of that sample, we get something that looks like this. Now, for one individual atom, you can't tell exactly when it's going to decay, but if you look at enough of them, you can see that there's this kind of trend, and the half-life is the time it takes for half of that radioactive sample to decay, or the time for the activity to drop to half of its original amount. So here we've got the half-life along the bottom. And of course, we know, I'm just going to go back over to here, that the activity is going to be dependent on the number of radioactive isotopes and this decay constant, which is lambda. Okay, and also this activity is just equal to the number of particles that decay per second, and that's equal to minus lambda n. Okay, there's also the activity is equal to the natural log of 2. So the decay constant is equal to the natural log of 2 divided by the half-life. And this is something you can actually derive from the equation that says n is equal to n naught e to the minus lambda t. Okay, now again, these are given to you in your data book. There's a derivation about half-life that I think I've got here somewhere. Again, if you want to download this, I'll put a link beneath the video. I've got and it's just rather a nice one, I think, because you can go from this to this, because what we can say is when n is equal to a half of n naught, the value of t is going to be the half-life, so t a half. So where do I have this? Gravitational field strength, slits. It must be here somewhere. Just before capacitors. Here we go. Yeah, so basically, if you're looking at the activity of something over time, the time when it goes from the initial activity to half that amount is going to be equal to the half-life. And therefore, from this, we can say that A over A naught equals e to the minus lambda t. The time is a t a half. A over A naught's a half, and therefore the natural log of a half, or minus the natural log of a half, is the same as the natural log of 2, which equals lambda t, so it's all there. Okay, right, this live stream is not the quality it was when I started. I'm getting a bit fatigued. But I think we've been doing it for 2 hours now, maybe, something like that. Okay, and it says derive and use the corresponding log equations. So I think for this, the important thing that all of you know about is that if you know that n is equal to n naught e to the minus lambda t. If you were to take the natural log of both sides, we could say that the natural log of n is equal to the natural log of n naught minus lambda t. Okay, and that's important because it means that you can maybe work out the value of this decay constant if you knew maybe the number of particles or the activity at certain times. That might then be plotted on the graph that might look like this, and the gradient might well be related to this decay constant. Okay, right, I think we've got two more things to do. Gravitational fields. People still watching, let me know how your revision's going. We've got gravitational fields and oscillations. I'm just going to quickly go through. Just going to get another sip of tea. Oh, by the way, if there's anything here that you don't understand and you want to see me explain properly, then I will be doing that. Well, I've got loads of pre-recorded videos over at A-Level Physics Online. Mr. Quarko, I'm going to be doing OCR-A tomorrow, so I'm going to do that on Thursday. Okay. Right. Gravitational fields. Basically, a field is just a region where an object experiences a force. Now, for a gravitational field, basically, it's something where a mass experiences a force. Okay, yeah, so that's all it is really. So if you've got a mass in this field, it's going to experience a force on that. Now the gravitational field is defined as F over m, and I would say that if you're doing Edexcel Paper 2, then this might relate back to some stuff you've done in Paper 1 looking at other types of fields. Okay, so the force per unit mass is our gravitational field strength. Also, if you've got two objects, so maybe this one's got a mass of m1 and this has got a mass of m2, the force between them, and again Newton's third law says that this force is going to be equal to that force in size but opposite in direction, the force between them is going to depend upon m1 times m2. It's going to depend upon the distance between them, which is r, and it's r squared, and then the constant of proportionality is big G, the gravitational constant. Now the way that Edexcel do it, they don't have a minus symbol in there, they just represent it like that. And that's Newton's law of universal gravitation. Now it then says about this equation here that says G is equal to Gm over r squared. Okay, now let's imagine, well, we know that, for example, the gravitational field strength G is equal to F over m. Okay, but the size of that gravitational force is going to be equal to this, which is G m1 m2 over r squared, and we're going to divide all of that by m. Okay, and let's call that m1. Okay, so that's the force on object 1. Now we can see here that m1's cancel, and therefore G is equal to Gm over r squared. And here m is kind of m2, it's maybe like the big object, the bigger object that we've got the field around. So this is the gravitational field strength due to that mass. And therefore G equals Gm over r. And that's the way that we've derived this. Okay, we then have a radial field. So if we've got this, maybe a point mass, there's going to be a field around it. Now, again, we represent field lines with arrows. The arrows in this case would all be showing the direction that a mass would move under this field. And so the field lines would all be going into this. And if you're going to draw field lines around a radial object, we want to draw at least 8. And they all meet at the surface like this. Now we can see that there's a denser, oh yeah, and this is like the field of M2. Yeah, that's right, Jack, yeah. Now we can see here that the field lines all kind of point in towards the centre. We've got a high density of field lines near the surface, and again this is in 3 dimensions, not just 2. Now we've got a stronger field here, and as we go further away, that field decreases. Now we can look at the difference in the gravitational potential, that's V grav, okay, and that's equal to minus Gm over r. Okay, so this is the other equation you need. Now, V grav is basically the gravitational potential per unit mass. Okay, yeah, so maybe this is like the field of M2, and we could look at the size of G at some point. Okay, and basically what we can look at is if we had a mass at this point, the gravitational potential per unit mass would be equal to Gm over R. Okay, and what's often important here is to think about how that changes and how it's this 1 over R relationship. So you get something like this. Now, what it's often more useful to do is think about how that changes as a mass moves, maybe from a lower point to a higher point in that field. Okay, and effectively, it's a negative thing because as something moves further away, that's going to get closer to 0. Okay, we then have to think about how this all compares to electric fields. Okay, now electric fields are the force per unit positive charge. Okay, and you can see how this and this are related. We also know that that force might be 1 over 4 pi epsilon naught times Q1 Q2 over R squared, and you can see how Newton's law of gravitational attraction is analogous to Coulomb's law of electrostatic repulsion. Okay, so don't forget everything you've done about electric fields and how this is analogous to these fields. Okay, and of course the last thing is about applying Newton's laws of motion and universal gravitation to orbital motion. So we might talk about, I think this is where this might lead on to, is if you've got an object which is moving around something else, then there might be a centripetal force here, and that centripetal force, mv squared over r, is caused by the gravitational force, which is gm over r squared. Okay, so you might think about, if this is object 1 and that's object 2, the force on that, the centripetal force is equal to m1 v squared over r, which is equal to the gravitational force of attraction. So you might have to equate those two things together. But also you might have maybe like a satellite moving around. You've got to think as well, if you've got satellites, the value of r is the distance between the centre of masses. So it's not the height of the satellite above the Earth or the planet, it's the distance from the satellite to the centre of that planet. But it's basically, the last statement's quite vague, and I think the only way you're going to get good at that is just by doing lots and lots of questions. Okay, so that was gravitational fields, and the last bit is some stuff about oscillations. Okay, so oscillations, simple harmonic motion. So, if you've got something undergoing simple harmonic motion, and I think that, again, just using pendulum is like the nice example of this. Basically, let's imagine it had a displacement x in this direction. The acceleration is going to be in that direction, okay? And the acceleration is going to be proportional to the displacement, but in the opposite direction. And therefore, we can say the acceleration is equal to minus kx. Okay, and this is the defining thing for simple harmonic motion, because the force is going to be this way when it's displaced to the left, and of course the force on that mass is going to cause this acceleration. Now k, a is equal to minus omega squared x. Okay, so omega is like the angular frequency. So there are loads of equations. Okay, you need to know that omega is equal to 2 pi f, which is this thing up here. You need to know that, what have they got? They've got a load of things, okay? Of course, the time period is equal to 1 over the frequency, and that's equal to 2 pi over omega, because, so is that right? So 2 pi over omega, because 1 over frequency is equal to 2 pi over omega, so it's basically taking that and just putting it into that format. The other ones are that x equals a cos omega t, v is equal to minus a sine omega t, and a is equal to minus a cos omega t. Now I think writing it down like this is really important. You basically take x, you differentiate it with respect to time to get v, differentiate it again and you get a. And of course you can see that a cos omega, so I should have an omega in there and an omega squared. You can see that a cos omega t is that, and therefore that's also the same as a is equal to minus omega squared x, because all of this here, a cos omega t and a cos omega t is the same. So this thing here is kind of what we saw up here about that defining equation for some harmonic motion. And this here is basically, if we think about the displacement time graph, if it's a cos graph, it does this, doesn't it? Okay, so that's basically saying at time equals 0, the displacement of that is equal to 0. Okay, and that's why we use cos for that. Okay, you can also do something similar with a sine omega t, but that's where you start at a certain value. Is that right? I've forgotten which is cos and which is sine. Ah, cos 0 is 1, isn't it? So, okay, so at time equals 0, x is equal to the amplitude. Is that right? Someone in the chat tell me. So yeah, that's a cos graph, isn't it? Oh, hold on. I've gone too long. I've completely forgotten some basic stuff. Yeah, that's right. Good. Right. Just having a brain fart there. Okay, so yeah, so that one there is a cos graph. So that's y equals cos x. And if that's a cos graph, when t is 0, the displacement is equal to the amplitude. Okay, and that's why we start with this one here, a cos omega t. So that's kind of like saying we pull back the pendulum, and at time 0, when we start the clock, we're at maximum displacement. We start the time when it then goes back and forwards. Okay, now the other two things you need to know about are, if you've got a pendulum, then the time period is equal to 2 pi root L over G, and that's for a pendulum. And the other one is that the time period is equal to 2 pi root M over K, and that's if you've got a spring mass system which is oscillating up and down. Okay, so these are the two kind of classic examples, and most things can be modelled either as an oscillating spring system or an oscillating pendulum. Okay, we also know from this thing over here, and actually this is the kind of displacement time graph. I'm just going to draw that again. I'm going to draw 3 of them. Okay, if this is our displacement time graph, that's velocity time, and that's acceleration time. If we start with a cos graph, the gradient of this line is going to be equal to the velocity. Now, when the gradient is 0, the velocity is 0. We then have a maximum negative gradient down here, so that's going to be our maximum negative velocity. Then we've got 0 gradient, and then we've got maximum positive velocity, and effectively that's why we go to something like this. Okay, and then of course if we differentiate that again, we then get a minus cos graph, which looks like that. Okay, is that right? So basically this is this, this is this, and this is this, because what we've got is our displacement, velocity, and acceleration time graphs. Okay, and the, yeah. Right, I think that's all right so far. The next thing we've got is resonance. And basically when the driving frequency is equal to the resonant frequency, we get maximum oscillations, and we get something that resonates. And we get a graph that looks like this. So we've got our frequency along here, we've got the amplitude of the oscillations over here, and what we find is at a certain frequency we get maximum oscillations, and this is an example of resonance. And what we try and do is we try and reduce that as much as possible by damping something. Okay, right, I'm just going to see what it says here. Yeah, I think that's it. So basically, this is a graph you need to know about. You need to know about how when you damp something down, we not only change the natural frequency, but we also change the amplitude and maximum oscillations, and how this graph kind of sort of shifts down to the left, I believe. And free and forced oscillations, I think that's all right, isn't it? I think we've kind of done it. The last few statements on the spec are just quite wordy. It's like how to apply conservation of energy to damped and undamped oscillating systems. I guess we're going to have energy is going to be dissipated in a damped system, because some of that maybe kinetic energy is going to be transferred to other stores. Free oscillations will oscillate at their natural frequency. Forced oscillations will just be ones where there's this constant input of energy. Yeah, I think the last bit is just kind of quite wordy. So I think that's kind of it. So I reckon that was Edexcel Paper 2. How long has that taken? About 2.5 hours. Oh, I've got to do it again tomorrow for OCRA and again on Saturday for AQA. So I think that's been useful. Now, of course, that was just a really quick whistle-stop tour. There's so many more things I could have added to that. I would say that if you're still watching this, well done, by the way. I would say that if there's anything you're not sure about, you can go over to alevelphysicsonline.com. If you go to the Edexcel page, then there's more videos there that kind of explain all of that stuff properly and in a bit more detail. But of course, the biggest thing between now and your exam, you've got over a week probably, depending when you're watching this, is just doing as many practice papers as possible. Some of the concepts are relatively straightforward, but it's applying that knowledge in a new, unfamiliar kind of scenario, which is often where it's a little bit more tricky. And the only way to get good at that and more confident is just to do as many possible questions as possible. If you're doing Edexcel, then you do have the current specification past papers. You've got AS papers that you could have a look at. You've got old spec Edexcel papers, and also what's really good is you've got the Edexcel International A-level papers. They're going to be very similar. The specification's almost identical. The language is often a bit easier because it's often meant for students where English is an additional language. And so Edexcel International A-level papers are a good bet and a good source of questions as well. So yeah, that is it for this stream, and I hope all of you do really well in your exams. And I will be doing many more live streams over the coming weeks, ready for paper 2 and paper 3. So thank you so much, everybody, and goodbye.